So welcome to part 2 of our investigation of vector fields. I'm sorry it took me so long to get this video posted. I had some technology troubles, which anyway. So right now I'm at the D2L homepage, and at the bottom of the course content page we have our online technology resources. And under this list of resources I organized it a little bit by chapter number. And the first link that we have here is a basic vector field plotter. So this is something that we've seen before when we were talking about gradient vector fields. And when you open that, you see that you can plot whatever vector fields you want. Notice that they're always two-component vector fields, meaning that my inputs are points in R2 and my outputs are vectors that have two components. One thing that I want to note is the notation here, that the first component, so when I write a vector that typically looks something like maybe x comma y, you'll see that this isn't accepting that as a vector output, that we get an unknown operator, that we have to write it in terms of i's and j's. So xi plus yj is an input that this plotter will recognize. And really what I would like to demonstrate is some of the things that you can do to mess around with this to make things look differently. So for example, if I were to put a negative sign in front of this x, which is the x component, what is that going to do? A negative sign in front of this for my first component function is going to take, instead of all of the arrows pointing outward, it's going to flip the orientation as far as left and right. So I'll put that negative sign and see what happens. These arrows that were previously pointing out to the right are now pointing back to the left, and these arrows that were pointing out to the left are now pointing back to the right. Similarly, if I did that by putting a negative sign in front of the y component, anything that was pointing up is now pointing down, and anything that was pointing down is pointing up, which is what you might imagine. Another notational thing that I'd like to add, suppose we want to look at something like x plus y as our component function in this first component. This does a whole bunch of different things to our graph, but I want to note that you need to make sure that you have parentheses around it so that it's considered as the first component function. Looking at something like x plus y, this is just in the x component. So in this first quadrant, x plus y is going to be a positive value because both of them are positive, and we see this first component is dictating how far it's pointing over to the right. And we see that that value is greater now than it was before when we just had an x. Conversely, here you can sort of, well, the x's are negative and the y's are positive, and so to a certain degree they'll cancel out, meaning that right along the line where y is exactly equal to x, you aren't going to have any motion. Maybe that's what these arrows are that are pointing exactly vertically. They're pointing exactly vertically because they aren't pointing to the right or to the left, because this first component function is telling you how far you should point to the right or point to the left. So really, I guess all I wanted to demonstrate was notation for being able to input these vectors into this vector field, and playing around with it to develop a little bit more intuition about what happens when I plug values in. Whoops. So, whoops. I know. So you can even do crazier things. One last thing that I want to point out, maybe this is my sine of x, maybe cosine of y. Let's make it interesting. I type this in and you can see all these little arrows pointing different places, but it's hard to get a feel of what the graph is doing. So another capability that this has, down here in the Windows settings box, I can look and I can change the scale of the arrows. So right now the arrows are really, really short so that I can fit in more arrows onto the screen. But if I make these arrows a little bit longer, I just clicked 0.5, making the little arrows longer, in this case, gives us a better visual of what's going on in the space. I can even make the arrows up to full scale of length, and at least for me, this is something that's helpful, that you see the periodic nature of the fact that if I have sine x in the x components, my arrows are going to alternate from pointing left to right to left to right, and cosine y, they're also going to alternate pointing up and down and up and down in a periodic way. I can also zoom in. Let's say that I don't want to have my brackets from -10 to 10. Let's say I just want to look from 0 to 4, and also from 0 to 4 along the y-axis. This gives us a nice zoom into just one of those Oh, now our scale of 1 is a little bit too big for those arrows. I can't really tell what's going on because there are too many arrows. Let's see that. So now the arrows are a little shorter and we get a better perception of just one chunk of the periodic nature of this 2D vector field. So going back to our technology tools page, there's another vector field plotter that we have here. It's the 3D vector field plotter, and this is the one that I've had trouble with technologically trying to implement. And so it may be the case that you can't get this applet to work on your computer. And so here's an example where you can look at this without actually having to do it on your computer. One of the things about notation in this, if you do have a function, such as a sine function, you need to use square brackets rather than curly brackets. But if you just have a simple function, like a function x, y, and z, this is saying that my inputs are points in R3 and my outputs are going to be the vectors that exactly represent that point in space. And I can click View Evaluate Static, and that'll give you a static picture. And I think that most computers will be able to visualize this statically, but sometimes the picture is confusing. You can't really tell what's going on. Evaluate Live, it launches this Java applet for you that allows you to click and rotate so that you can get a better idea of what's going on. And notice that in this case, near the origin, my vectors look a little like the vector 0, 0, 0, and as you span outward, your vectors are always pointing in the positive direction because this is just the positive first quadrant. I could change the range of the quadrants if I wanted to. So if I went from negative pi to pi, that's sort of a funny range given that we aren't dealing with trig functions. But then the origin will be in the center of this plot. We see that everything is diverging outwards from 0 for this three-dimensional plot, which is cool. Yeah. And that makes sense, because depending upon where you are in space, that vector is going to point in exactly the direction that corresponds with its x, y, and z coordinates. Let's say that, for example, I decided to switch some of these. Let's say I switch my x's and y's. How do you think that that will affect the graph? Well, let's take a look. Clicking Evaluate Live. We see some interesting behavior, and it's hard to see this clearly, but that twisting shape that we had before, so this is sort of my bird's eye view that we had previously, only our z values are continuing to grow upwards. So this is an applet to play with and look at. I actually think that in some ways it helps to visualize the space, but for me, plotting actual points is sometimes an easier way to visualize what the space looks like in 3 dimensions. Visualizing 3-dimensional vector fields is something that's a challenging task. That's all I wanted to share. Thanks.